Today we said that we were going to do examples of redox reactions to see what oxidizes and what reduces, to gain some practice, and in terms of electrons and oxidation states, which we introduced in the last lesson. And here in this screen, I have a reminder of the past when we spoke about what is oxidation and reduction, and we saw the old definition of oxidation and reduction and the modern one in terms of electron transfer. In the old definition, oxidation was gain of electrons, gain of oxygen. It was in terms of oxygen, in terms of gaining and losing oxygen. So oxidation is the gain of oxygen, is the gain of oxygen, and reduction is the loss of oxygen. In the modern understanding of oxidation reactions is that oxidation is the loss of electrons, and reduction is the gain of electrons. In other words, in the modern understanding of oxidation reactions is a matter of transfer of electrons between different species in a reaction. So we, of course, from now on, we're going to stick to electrons and the modern definition in terms of gain and losing electrons. And we spoke, we did a couple of examples last week, like we spoke about this example of zinc reacting with copper sulfate, in which case the zinc replaces the copper, and we saw what oxidizes and what reduces, and we wrote this as an ionic reaction. And in the process, we also introduced oxidation states, oxidation numbers. And we spoke a little bit about oxidation numbers, if you remember this page, in which we said that group 1 elements, these metals from group 1, usually are assigned the oxidation number of +1. The metals of group 2 are assigned the oxidation number of 2+. And on the other side, the non-metals, the halogens here, group 17, are assigned the oxidation number of -1, whereas in the previous group, starting with oxygen, the group 16, they are usually assigned the oxidation number of -2, but there are exceptions, and in between, like the transition elements and also some of these here, especially this group of carbon, starting with carbon, the oxidation numbers might change from compound to compound, but as we go along and we meet such cases, we'll see that. So to begin with, roughly, we are going to initially we're going to see examples where the oxidation number of some species in an equation, like this one, for example, could be considered to have the same numerical value as if this item was an ion, and what would be its charge. Usually this is the same with the oxidation number. We also said, and this is very, very important, that when we have an element appear in an equation, like here, this copper, which is solid, and this oxygen, which is in the gaseous state. These are elements. Elements are assigned 0 oxidation number. So the oxidation state is 0, always in elements. Whenever we see elements like here, this is an element because it's hydrogen gas and this is oxygen gas. These are always assigned the oxidation number 0. But if they are part of a compound, like this one is a compound, copper oxide, then we assign them an oxidation number as if, which we call the oxidation state of this atom, as if we pretend that this was an ion, and what would be the charge of this ion? Usually the same is the oxidation number that we assign to it. Which is not a problem if a compound is an ionic compound, because an ionic compound is made out of ions. But there are other compounds which are not ionic, and in this case we pretend that they are ions to assign them their oxidation numbers. So let us start. I have put together some reactions, chemical reactions, which some of them we have seen before, just to get us starting and practice finding what oxidizes and what reduces. Okay. Sorry, let me. Yeah. Okay. So what do we have here? We have copper solid reacting with oxygen, and the product is copper oxide, which we have seen before. We said that the copper oxidizes because it gains oxygen. And now we're going to see why the copper oxidizes in terms of oxidation numbers and transfers of electrons. And also we're going to see now what oxidizes and what reduces, because previously, if we were talking with oxygen only, we could see that copper oxidizes, but then what reduces? And we said that in a chemical reaction, if something oxidizes, something else reduces. These two, oxidation and reduction, always go together. So now we can understand, we can find out what reduces here with a modern definition. So let's see, we assign oxidation numbers, and let's see, we said copper is an element, has an oxidation number 0, oxygen 0. Now here in the copper oxide, oxygen always has the oxidation number of 2 minus, unless if it's part of a peroxide. But we are not going to be wrong if we always assign the number 2 minus, okay? The only time where it has a different oxidation number, the oxygen, is in the hydrogen peroxide and other peroxides. But only if we see that here, it's an exception. It has the oxidation number of 1 minus instead of 2 minus. But anywhere else, it has the oxidation number of 2 minus. Okay, so copper here has the oxidation number 2 plus. Also, if we're not sure if we have assigned the correct oxidation numbers, we need to remember that if we add the oxidation numbers, because it's like representing charges, if we add them, they should give us the sum should be 0 if we talk about a neutral compound like here, unless if this is an ion, then it's a different story. Then the sum should have the charge of the ion. But now this is a neutral compound. So if oxygen has an oxidation number of 2 minus, copper must have a 2 plus. All right, so let us see now. So copper, we see that from an oxidation state of 0, ends up in an oxidation state of +2, isn't it? From 0 it goes to +2. That means it increased. Its oxidation state increased. This is what we call oxidation here. Copper oxidized. Now, we knew that because it gained an oxygen from the old definition. Now, let us see what else here changes oxidation state. And of course, it's the oxygen, because when we see an element, this has an oxidation number 0, and then we see it in a compound, obviously it has changed. So oxygen now, from 0, the oxygen has changed oxidation state from 0 to 2 minus 2. It's right, it has numbers. So from 0, it has gone to -2. Its oxidation state decreased, it reduced. So we can see that here, this is what reduces. The oxygen reduces, which means it's the oxidizing agent. The copper oxidized, which means it's the reducing agent. Of course, when we see oxygen, things reacting with oxygen, we know that oxygen is always reduced in redox reactions because it's a very, very strong oxidizing agent. The mother of all oxidizing agents, apparently. Anyway, so yeah, so there we see that one thing oxidized, another thing reduced, and now we see why we have both reduction and oxidation reaction. With a new definition, in other words, this is possible. It is possible to identify which one reduces and which one oxidizes, looking at the oxidation states. We can also talk about the transfer of electrons here. Which one took electrons and which one gave electrons? Because obviously in redox reactions there are some electrons kind of transferred. So since, okay, from copper, for example, copper from 0, its oxidation state increased to +2, which means it's like its charge became positive from 0, from neutral, which means it gave away electrons. So we see that copper gave away electrons, and these electrons were taken by oxygen here. There's always a transfer of electrons, and it's nice to figure out what gives and what takes electrons, because in the future we'll need to write this oxidation and reduction half reactions in terms of gaining and losing electrons as well. But now let us see what else do we have here. This water, I think somebody had asked about this equation. Where is the oxidation here? Where is the reduction, isn't it? We see the water loses oxygen. Obviously, it reduces in the old definition. But now, let us see now with oxidation numbers. Well, hydrogen and oxygen are elements. Obviously, the oxidation numbers are 0. The oxidation state is considered to be 0. And here we see that hydrogen and oxygen are part of a compound. Obviously, they have different oxidation numbers than 0. So we can see why this is a redox reaction. So let's see now, oxygen has an oxidation number of 2 minus. Hydrogen always has +1. So we see that for the hydrogen, let's write for the hydrogen and for the oxygen, which are the two things that have a change in oxidation numbers. There's nothing else actually. So the hydrogen from +1 here in the compound, from +1, its oxidation state went to 0. So it reduced. So +1 to 0, its oxidation state reduced. So hydrogen reduced. It's the oxidizing agent. The oxygen, on the other hand, from 2 minus, from -2, let's write it as a number, went to 0, increased, isn't it? From -2 to 0. This one increased, which means if it increases, means that this is what oxidizes here. Oxidized, it was oxidized. So the hydrogen reduced from +1 to 0. The oxygen in the same compound obviously was oxidized from 2 minus to 0. So we see what is reduced and what is oxidized. The reduction and the oxidation again took place together. So one element from the same compound was reduced, the other element was oxidized. So I hope you can see that these two, oxidation and reduction, taking place at the same time again. This one also, we have seen it before. Copper oxide plus reacting with hydrogen. We see hydrogen's an element, so it should have 0, also copper too. When we see metals on their own, obviously these are elements and they are solids here. Anyway, let us ignore now for the time being the states. Now, all right, so already we can see that certain things appear as elements with oxidation number 0, and the same things are also part of compounds, which means that their oxidation states are other than 0. So obviously this is also a redox reaction. Now let's see, what else do we have here? Let's see, copper here, copper. Copper here, if oxygen has an oxidation state of 2 minus, always, copper must have an oxidation state of 2 plus in the copper oxide. So we see that copper from 2 plus went to 0. Its oxidation state from 2 plus 2 decreased to 0. So this is a reduction here. So copper reduced. Reduction. The copper was the item that reduced here. And what else changed here? Let's see, the oxygen from -2 here. What is the oxygen here? It's also 2 minus, isn't it? Then the hydrogen from 0 in the reactants has gone to +1 in the water. So we see the hydrogen also changed. So the hydrogen from zero, its oxidation number increased to +1, to the +1 oxidation state. So this was oxidized. This was oxidized, which means that the hydrogen oxidized because it's the reducing agent, whereas the copper was reduced, which means it's the oxidizing agent. What else did we have here? We also had oxygen here. You see, the oxygen, its oxidation state did not change. Did not change. So nothing happened to it. Did not change. So usually two other things that change oxidation state in a chemical reaction. One oxidizes, the other one reduces. The rest do not change. Okay, so in this case, you see the oxygen did not change. In other reactions, the oxygen oxygen changes oxidation state, especially if it's a gas. If it reacts with something like a oxygen gas, then it's a very strong oxidizing agent. It's the one that reduces. But in this case, it did not change. It was just a spectator. Okay. Why is this so hard? This one, the zinc and copper sulfate, we also saw it in the previous lesson. And we have the zinc replacing the copper. And what do we have here? Now, here is the same reaction, but the ionic equation of this reaction that includes only the items which are oxidized, oxidized or reduced. The remaining, which are spectators, are not considered. So let's see this reaction, the proper reaction here, the complete reaction. Zinc here, being an element, has an oxidation number 0, and here copper has an oxidation number 0. Came out from the solution. So zinc here with a 0 oxidation number, and in the products, we see that zinc is part of a compound now. So obviously, the zinc now has changed oxidation number, oxidation state. And in this case, it's actually 2 minus, okay? It's 2 minus because the sulfate ion, sorry, 2 plus, not 2 minus, 2 plus, because the sulfate ion has an oxidation number of 2 minus, isn't it? So this is 2 plus. I'll write it clearly because I messed it up. So zinc here goes to 2 plus, its oxidation state. What else? The copper. Let's see the copper, because we know that the copper must also change oxidation state. Here must have a different oxidation state than 0. So copper here is also 2 plus, 2 plus, because the sulfate has an oxidation number of 2 minus. All right. So zinc from 0, its oxidation state changed to +2. So it increased, it's oxidized. And copper from 2 plus, +2, let's write +2, its oxidation state changed to 0. From 2 plus to 0. So this was reduced. So we see again the oxidation and reduction parts of the reaction. And you see the sulfate ion did not change any oxidation state. It's a spectator. That is why when we write, if necessary, to write the ionic reaction, in which case we all only kind of illustrate the reduction and the oxidation have reactions without ignoring all the other spectators that don't change. So what we write here, the zinc, let me write it here where we have more space. So zinc, this zinc plus here is the copper that changed oxidation state. So I only write the copper ion, ignoring the sulfate ion, so plus copper, but I must remember to write its charge, because now this is an ion. And the result was, we have zinc sulfate, but I'm only going to write the zinc ions here because this changed, zinc changed oxidation state, and that was 2 plus, and plus copper element, copper metal. So this is the ionic reaction, so in the ionic equation. So the ionic equation, in other words, if they ask us, write down the ionic equation, concerns only whatever oxidizes and whatever reduces, leaving out the spectator ions. Okay, so up to now. Guys, if you have any problems and you don't understand something, or if you want me to discuss something else, you can write me a message because I can see the messages now. Okay. Let's do something more complicated. Let me see what other reactions examples we have here. We have 5 minutes. So I left some space here to do some more problems. Like we could, something interesting. Yeah, let us discuss. Yeah. Because we have seen in the past combustion reactions. You remember we had said that hydrocarbons reacting with oxygen, we call it a combustion reaction, and the result is carbon dioxide and water, or the fuels that we burn. So let us see now the methane reacting with oxygen, which is the combustion reaction of methane. The result of the complete combustion reaction is always carbon dioxide and water. All right, so okay, this is a 2 times 2, 2 here and 2 there, then 4. Okay, I think that is all right. Now let us see now what, because we said all this oxidation reaction, because this is an oxidation reaction with the oxygen. They're always, if there is oxidation taking place here, this must be an a redox reaction, because whenever there is oxidation, there has to be a reduction as well. So let's see. So again, how do we start? We start by assigning oxidation numbers. Otherwise, we cannot do. We'll get confused. Okay, oxygen here. Oxygen is an element here. We'll have the oxidation number 0. Okay, we have no other elements. The others are compounds. Let's see now. Let's see carbon and hydrogen here. Hydrogen always takes the oxidation number of +1, oxidation state of +1, always. So if this is +1 here, because we have 4 hydrogens, the oxidation state of carbon in this compound, in the methane, then must be 4+, isn't it? Because remember, the whole compound must be neutral. So 4 atoms, each with +1 oxidation state, plus the oxidation state of carbon, altogether must give us 0. That is why how I found that this carbon here has an oxidation. Oh, not plus, minus, goodness. Dear me. 4 minus, not 4 plus. 4 minus. Because you see, the sum of these charges must be 0 in the same compound. So if the carbon has a -4 oxidation state, and the hydrogen, each hydrogen has a +1, but we have 4 hydrogens here, so 4 times +1, this should give us 0. That is why I knew that this must be -4. Okay, so that was a parenthesis. You will not be asked to do such complex things here, but I just told you how I know. I just want us to see that this combustion reaction is also a redox reaction, as we said. as we had said in the past. So anyway, 4 minus and here plus 1. Now, what happens here in the oxygen, in the carbon dioxide? The oxygen here has an oxidation number. Oxygen always has 2 minus. So in this compound now, the carbon, obviously we can see it must have a positive oxidation number, whereas here had a negative. Already we see that there is a change. So what must be this number here, this oxidation state of carbon? So it must be 4 plus in this case, because 4 plus 2 atoms of oxygen, each with a 2 minus state, altogether gives us 0. And what happens here in the water? The oxygen always has a 2 minus. The hydrogen always has a plus 1. We see the hydrogen does not change from plus 1 to plus 1, does not change, it's a spectator. But the oxygen, yes, the oxygen changes. Look at this. The oxygen changes from 0 to minus 2 in both cases here. And the carbon also changes from minus 4 to plus 4. So carbon and oxygen change. The carbon from an oxidation state of minus 4 jumped to plus 4, increased, this oxidized, oxidizes. And we can see that it oxidizes. If we think in terms of gaining oxygen, you can see that the carbon gains oxygen and becomes carbon dioxide here, isn't it? So we knew it oxidizes. Okay, so carbon oxidizes, and now we see why in terms of its oxidation numbers. The oxygen now from 0 here, from zero, it jumped, dropped to minus 2 in both of these compounds. So the oxygen reduces, and of course it reduces. We would expect it to reduce because the oxygen is a very, very strong oxidizing agent. And a combustion reaction is an oxidation reaction. It's a very strong oxidizing agent. So there we see the reduction and the oxidation that take place during the combustion of methane and other hydrocarbons similar. So there we saw another case. Listen, this was difficult, but I just wanted you to see that this is also an oxidation reduction reaction in terms of the new way of looking at the redox reactions, okay? Is zinc the reducing agent? Let me see, you're referring obviously to a previous reaction. I suppose you refer to this reaction, eh? Yeah, zinc here is oxidized, which means this is the reducing agent. And copper is reduced, which means it's the oxidizing agent. Exactly, yeah. Remember, what oxidizes is the reducing agent. What reduces is the oxidizing agent. I hope I said it right. All right, so I hope we had enough examples. Don't be confused with more complex cases. It's just I wanted to see that wherever there is a reduction, there is an oxidation, and the role of the oxidation states, all right? So now we have to stop, unfortunately. I hope it makes sense, people. I hope next week we can do something different to move on, okay?